Graph NNNs learned by exchanging information with neighbors. So how this works is a GNN updates an embedding vector that it has that is a conversion between its information that it has gathered from all the different neighbors to a vectorized representation. And so this is called message passing, where a node learns by exchanging information with other neighbors. So every single node has a vector or an embedding, which is a contextual representation of what the node represents. So not just numbers, but contextually, what does that node represent? What is the meaning of that node? And that meaning is defined from the information that it gets from its own neighbors. So every node has a vector and embedding, and GNN updates that vector by looking at nearby nodes. So it looks at what information do other nodes have that are my neighbors, and it combines their information. And it combines their information at every step. So it has a hidden state, and then it updates that hidden state with the information it gains about its own node, right? About itself, along with its neighbors, the nodes of its neighbors. So this is what we call message passing, where a node is able to send its information with and exchange information with its neighbors. So now what is the input in this? So we have nodes, which represents the entities themselves. So people stock web pages, molecules. We have edges that represent friendship, correlations, links, chemical bonds, and then every single node may have a feature. And edges can also have features as well. And then the main GNN update rule is this message passing, where each neighbor sends a message, and this message is a representation of what that node semantically mean, or what meaning that does that node have? What information is it able to pass? So each neighbor sends a message to the central node, right? So a node has X number of neighbors. The neighbor sends a message to that node in each layer. The node then aggregates all the incoming messages, and the node then updates its own embedding, and that own embedding is updated through the hidden state. So a node has a hidden state. It captures the hidden state of other nodes, and it updates its own hidden state after exchanging information with its neighbor nodes. And so this occurs through multiple layers. So after the first layer, a node knows about just its own neighbors. Second layer, neighbors of neighbors. Three layers, and so on. And so when you have a dense number of layers, you're able to understand the node, you're able to get a contextual representation of what of the network that the graph has. You're able to learn more about the nodes of other nodes and the neighbors of nodes. And so if nodes are people, edges are relationships. For friendships, you're predicting whether someone likes basketball. You're predicting their own features matter, but also their friends' interests also matter. So if it's not just the node itself, but it's also who is associated with that node, that also can determine the node's features. So if you're trying to classify a certain node, yes, you need to know node properties. You also need to know the other features of the neighbors of that node. And so GNNs can predict node classification, graph classification. You can classify entire graphs as well. So classify a molecule as toxic or not. You can represent an entire graph as a molecule, and you combine all node embeddings into a single graph embedding. You can predict links, relationships between nodes. What will this link or this relationship between node X and node Y be, given the attributes of the ending and starting nodes? And so message passing is like nodes talking to each other. Each node has some information that it then passes to its neighbors, and it receives information also from its neighbors as well. And so each node, after it gets information from the neighbors, it combines its own information and the information that is received from other neighbors to make an own embedding. And this works because through the layered process that we talked about. So GNN learns, it updates each node using the information from its neighboring node, message passing. Suppose now we have a table of these different sales, and now we want to do a group by, but in the group by, we also want to make sure that we don't condense the rows, right? If we group by region or salesperson, right, we are going to get Alice, and that is, if we only group by a salesperson, Alice is going to be the only row. So we're changing and condensing the rows. But if we don't want to change or condense the rows, if we just want to have salesperson region sales and we just want to have a single row, this row being unchanged, but still calculate a grouped calculation of, say, you want the summation of uh, Alice sales or summation of Bob sales, you or the average Alice or average Bob sales or average East or West region sales, and you can have that as an average column here, and you can have that as a value without changing or without condensing the number of rows. So that is over partition by. Partition by is what is mental model is what are you grouping by where you want to have a single row? What are you grouping by where you want to have a single row, right? So that's what we have here now. Now there's rank and there's also dense rank. There's rank and dense rank. If we want to do a rank after we do a partition by, in the partition by, you can think of this as group without condensing the rows. Group by without condensing the rows, that is over partition by. Now, when you do a group by, you may also want to do an ordering. Now, and you do an ordering in the partition by, there's two types of orders. There's rank and dense rank, and those differ in terms of how they deal with ties. Rank deals with ties that if there is a tie, the next rank will be 3. This is typically not what we want. We typically just want dense rank. So if there is a tie, then both are 1, and then the next rank is 2. So we typically want dense rank, and that is typically the use case is we want dense rank. So we do rank over partition by order by sales descending. Order by sales descending. So the highest sales in the region, within that region. So within the East region, the highest sale is 700. So that's going to be 1. And the next highest sale, right, it is also 700. That's also going to be 2. Now the next unique value is 500. Now for our rank, it's going to be 3. For our dense rank, it's going to be 2. So dense rank 1 to 2. Rank is just 1 to 3. Right, 1 to 2 versus 1 to 3 is how you can easily remember that. Docker as a tool makes it very easy to run software in containers. Also, like a package, you can take that package anywhere you go, whether it's on a boat, on a ship, on a lighthouse, on Earth, on Mars. You can take that package and it will work wherever you go, no matter the location. That is what a container actually is. You package your entire software and entire apps. You include the dependencies, version control, etc., into the single container, so you don't have to deal with version conflicts or environment issue. You're able to run that software wherever is needed. And so it's like a box that holds your app, everything it needs and everything. So it runs the same anywhere. A container is that running instance of your app. Docker is the tool that packages everything into the container. It's a platform. It's a tool that makes easy to run software in containers. Now, container is that running instance of that app. Container is that running instance of that app. So an image, and then an image is the blueprint or the recipe. How can you actually create the app? So you have the box. How can you actually create whatever is inside of the box? And that is through the instructions manual or through the blueprint or through the recipe. If you're making food items, through the recipe that you actually make the item. So it's through the image, which contains the blueprint, that you actually are able to create. Then the container, which is the running instance of the app. So the image is the blueprint, the container is the instance of the app that is created from following the instructions of the image. A registry is where those images are stored and shared. And a rancher is a tool to manage containers across many servers. Kubernetes is an entire container orchestration system. So we have containers, right? But how do we know which nodes and which containers run on which nodes? You can have 100 different containers. You can have 100 different running instances of that image. And if one server goes down, how do we allocate, okay, this next server so that it should then run this container? And that is the entire allocation of resources and allocating which containers run on which servers. What Kubernetes does is orchestrates the entire container system. And now, what is the tool that Kubernetes can use? It is Rancher that identifies all of the different across all of the different Kubernetes clusters, what are all of the containers, and it makes it very easy to scale containers, stop containers, easy to start. So you can think of an analogy as the Kubernetes is like a robot chef that ensures the right number of cookies and foods are always baking and distributes them to ovens. But the rancher is keeps track of all of the different cookies baked on many of these different ovens, which are represented metaphorically as servers or servers are metaphorically as our ovens. And so Rancher orchestrates and manages Kubernetes. Kubernetes orchestrates and manages the containers themselves across different worker nodes. So you make a Docker image, push to a registry, run it as a container. Rancher, Kubernetes manage many containers. Rancher is optional. So it's a management tool. See all clusters, containers in one place. Deploy apps without writing tons of commands. You don't need to write every single command to stop a specific cluster, scale up or down. You're able to, it's a very nice UI, easy interface that Kubernetes can use to see all clusters and containers and makes it very easy to deploy apps without writing commands. And you can even manage multiple Kubernetes clusters across different servers through Rancher. Spark ML transformers estimators. Pipeline estimator is like the machine that can be trained, and it is the output of it is a model, a learned model, and that can be applied because that learned model is a transformer. Now it can be applied since it has learned a set of rules, it can be applied to data. And so that is standard scaler. It has learned a set of the rules, right? How to standardize, how to scale, do standardization, and so it follows a set of rules. So and so it does the transformation. It is lazy. Transform is lazy, so it only executes when you commit an action on the dot collect, etc. Weights and biases. Main difference between W and B and ML flows. ML flow handles the deployment. It is a storage for the models. Weights and biases not necessarily storage, but it's more a way to track the experiments, visualize metrics, log hyperparameters. Save a model, you can deploy it as REST API, log metrics, versions, artifacts. So not only can you track the experiments, but you can also package and deploy the models through ML flow. Spark ML lib. So we have batch and streaming models. So this is the rate at which the predictions, when you have deployed your ML model, the rate at which the predictions runs on static data sets. That's batch. Streaming is live data streams, Kafka events, hyperopt, hyperparameter search. So not just random trial and error, but actually incremental versions where it gets better at selecting which hyperparameters you actually want to search. So it selects a number of parameters and it sees the performance and it sees, okay, this is the next best set of hyperparameters we want to possibly test. Not just random grid search, which goes through all of the different possibilities. Delta Lake, Delta Table, Delta Live Table, Delta data lake is a dump of all the data that we have. Delta Lake applies a versioning, ACID transaction, updates, deletes, schema changes extremely safely, adds a structure and governance layer. Delta Table is a table from that Delta Lake that is able to be queryable. It supports time travel and version control. Delta Live Table is not a table, but it's a pipeline that supports and keeps the Delta tables updated automatically. So storage format versus structured table on top of Delta Lake versus automated pipeline that actually creates and updates the Delta table. Kafka is like a conveyor belt. You have producers producing, sending the data, sending the clicks or the real-time data that is being ingested to a certain topic, and these topics are split by partitions. And a consumer can actually take those data by a partition, by a topic. Airflow is a scheduler orchestration tool that runs pipelines, keeps tracks of the DAGs, keeps tracks of the tasks, and executes them in order. It is a scheduler and orchestrator of these data engineering tasks. Table, we know what a table is. A view is a stored version of a query. A materialized view is a stored query result. A view is just a virtual table. It is just the query result. There is no actual storage, but a materialized view is the stored query result, and it is updated periodically. So a view is not an actual table. It is a virtual table where you almost store the query, but you don't store the query results. And a materialized view is when you run the view, when you run the query and you save those results and you store the query results. So clustered, non-clustered indices, cluster index, physically sorted by the index, so primary key, extremely fast retrieval. Non-cluster index you want to use when you want, it's like select star from where x equals 5 from a million rows. You want to use non-cluster index because the table order is unchanged. The index automatically points to the row, so it's just an extra lookup step. So the non-cluster is like the index card telling where you each book is. So you just look at the index card, so you already know where the book is instead of doing an entire table scan. So instead of doing a table scan across 1 million rows, you simply ask the non-clustered index, where is that one row specifically, and it points you to the not managed versus unmanaged. Managed Sparks owns the data and metadata. Unmanaged Sparks only tracks the metadata. So deleting table keeps the actual data. Spark jobs are lazy, meaning that they only execute when an action is called upon them. They define tags, they define transformations, filters, map filters. Those build the tag or recipe or sequence of tasks. We have the driver, we have the cluster, we have workers under the and executors. We have tasks that are needed to be completed, smallest units of works on partitions of data. So data is partitioned across multiple nodes, worker node 1, worker node 2, worker node n. Each of them does their respective jobs on their partition of the data that are then aggregated. The aggregated metrics are calculated and then finally returned. The cluster manager decides what work to actually assign each of these workers. And the driver coordinates everything, builds the DAG first on what the sequence of steps to do. Data partitioning is when you split data sets into partitions. Each partition is then processed in parallel. Entire LLMs and GPT at a very basic, the crux of them is next token prediction generators. What is the probability of the next token? And you repeatedly do that. And that's the underlying workings of GPT and these LLMs. So how does this work? How does the training and the testing work? It is these input tokens are converted to embeddings and positional encoding. So this is tokenization, converting words to vectors, and then embeddings having a contextual representation of what the meaning of the sentence is, adding positional encoding. So not just what the meaning of each word is, but where that word lies in the sentence. That is positional encoding, and associating a meaning with the ordering of the words. That is positional encoding. And so we have layers that learn those embeddings, and through backpropagation we update the matrices, learnable matrices, and that's the crux of LLMs. Next token prediction repeatedly. That's the crux. We'll stop there.